Okay, welcome to Friday. So I don't know if you're doing this before or after the assembly, but hopefully you enjoyed the assembly. And remember, you can always ask me questions. I finally had a couple of you ask me questions on Wednesday. And yes, I do get bored at home too, so make use of your time. I'm not saying ask a question, ask a question, but just reach out. Unless I'm helping someone else, I usually get to you, within 5-10 minutes. All right, let's see. 11, 6, 1 through 18 all. So 1 through 10 had two answers each. You were supposed to find the arc length and then the area of the sector. Okay, so on number 1, the arc length is 2 pi, and it said leave everything in terms of pi. Or did it say that? Sector describing in terms of circle, make a sketch, find the length. It does not say. However, for higher level math, rarely do we ever multiply by 3.14. We generally always leave our answers in terms of pi. Guess I probably should have pointed that out. But most of you guys check the back of the book anyway and see how the answers are going. All right, so number 1, the arc length was 2 pi, and the area of the sector was 12 pi. And once again, we're really lazy here on putting units. So arc length would be in units, and area would be in units squared. Okay, so I'll be lazy too. Number 2, arc length is pi, and the area of the sector is 2 pi. Number 3, arc length is 2 pi, and area is 3 pi. Number 4, arc length is 4 pi, and the area is 6 pi. Number 5, arc length is 3 pi over 2, and area is 9 pi over 8. Number 6, it's arc length is 1.2 pi, and the area is 0.48 pi. Now, that's probably one of the first ones you're like, wait a minute, how could area be smaller than the arc length? Well, just remember, two completely different units. One is units squared. Let's see. Number 7, arc length is pi. Area of the sector is 9 pi over 4. Number 8, arc length is 32 pi over 15. And area of the sector is 32 pi over 25. Number 9, arc length is 3 pi root 2. And area of the sector is 15 pi. Number 10, arc length is 16 pi root 3 over 5, and the area of the sector is 72 pi over 5. All right, so that was 1 through 10. Number 11, the radius is 6. Number 12, the radius is 2. All right, 13 through 18. Find the area of each shaded region. So these are the ones where you had just, there was some subtraction involved of some sort. So number 13, final answer is 4 pi minus 8. 4 pi minus 8. Number 14, 6 pi minus 9 root 3 all over 4. Now, if you had broke this up into two separate fractions, you would have gotten 3 pi over 2 minus 9 root 3 over 4. Number 15, 12 pi plus 8. Number 16, 18 pi minus 18 root 3. Number 17, 4 pi plus 6 root 3 over 3. If you broke it up into two fractions, it would be 4 pi thirds plus 2 root 3. Either one's fine. And the last one, number 18, is 9 pi plus 18. 9 pi plus 18. All right, count up how many you, I will promise you there will be at least one of those 13 through 18 on the test. All right, count up how many you got wrong. Put that on the Google Forms, question number 1. All right, Friday. Test next Friday. It'll be multiple choice test. I'll do a standard chapter review. And then it'll be a standard 50-minute test, multiple choice. All right, homework for tonight. All right, today we're going to do somewhat, I don't know, it's when you actually see what you do, it's not challenging at all, but to get there, it's a little challenging. Maybe a medium class today. Ratios of areas. Ratios of areas. Just one theorem today. All right, let's talk about ratios. Remember, ratios are two numbers compared using division, in other words, a fraction. And today we're going to be doing areas and ratios. In other words, our ratio is going to be made up of two areas. So they're going to give you some shape. It's going to have two of something. There's two triangles. Technically, there's three here. Two triangles here, a green one, and I don't know what color that is, yellow, orange, something like that. And you're going to be making a ratio of the two areas. So let's read what it says. What is the ratio of areas of two triangles of equal heights? So we're going to compare two triangles that have equal heights. So which two triangles there have the same heights? Triangle ABD and triangle CBD both have the same heights. Okay, so let's make a ratio. Now you have a choice. We could do green over. To me, that kind of looks orangey. You could do green over orange. You could do orange over green. We're going to do green over orange. Green over orange. So let's do the numerator first. Okay, let's find out the area of the green triangle. Well, the area of the green triangle is base times height. Looks like the base is A and the height is H. So base times height divided by 2, which would be AH over 2. Makes sense. The denominator is going to be the orange triangle. It's still base times height divided by 2. The base is B. The height is, well, it's H. And we divide that by 2. And we're going to do a ratio of these two. So like I said, you could do green to orange or orange to green. We're going to do green to orange. So the top one is green, the bottom one is orange. So that's my fraction one, green over orange. So see what I did there? Okay, well, we got a fraction over a fraction. We can do a copy dot flip. So numerator times the denominator flipped. Notice the 2's would cancel. And we would get AH over BH, and then the H's would cancel. I left that part out there, but I think you can see where that happens. So what does that mean? I just did the ratio of two triangles. I did the ratio of the areas of two triangles who had the same height, and check out what happened. What happens is, if that's the case, if you ever take the ratio of the areas of two triangles who have the same heights, you're left with the ratio of their bases. In other words, you're left with base 1 over base 2. Once again, two triangles. If we do a ratio of their areas and they have the same height, you're left with a ratio of their bases. Okay, it might be useful. Don't worry, we'll write this down. All right, let's do another one. Once again, we're going to do another ratio of areas. And this time, well, their heights are clearly different. One is H and one is K. So we're doing light blue, dark blue, right? But this time, we're going to do one where the triangles have the same base. The previous one, they had the same heights. We got that their ratio of their areas ends up being the ratio of their bases. This time, we're going to do a ratio of two triangles where their bases are the same. And want to take a guess what's going to happen? Okay, well, let's see if that guess was true. All right, same thing. Let's do light blue over dark blue. So light blue will be the numerator, dark blue will be the denominator. So let's see, light blue, the base would be B, and the height would be H, so we get BH divided by 2. And for the denominator, the dark blue one, well, the base is still B, but the height is K this time, over 2. We're going to do light blue over dark blue, so the top over the bottom. Do a copy dot flip. Notice this time the B's would cancel, the 2's would cancel, and you would be left with H over K. In other words, you'd be left with the ratio of the areas of two triangles that have the same bases ends up being the ratio of their heights. So those are two, we can't really say they're converses of each other, but certainly there's some similarity there. If they have the same heights, then the ratio is their bases. If they have the same bases, then the ratio is their heights. And remember, we're talking about areas here, okay? All right, we'll write this down a little bit later. Third one, a little bit more complicated. All right, before we do this one, we're going to be two triangles. They don't share the same base and they don't share the same height, but they are similar triangles. Previous ones, well, we don't know if they were similar or not, but these two are similar. So let's see, these two are similar, therefore we can write any corresponding sides in a proportion. Remember, we had that multiple theorems talking about if two triangles are similar, then their sides are in a proportion. I chose to write their bases and their height as my similarity statement. So let's see, I'm going little triangle over big triangle. So H of the height of the little one over the height of the big one, so that's H over K, would be equal to the base of the small over the base of the larger one. Does that make sense? And I just chose those those one sides and the height. I could have chose any one of the three sides. Okay. All right. We do have that one little statement. We're going to use that here in a second. Okay, so let's go back to what we're doing. We're going to do a similarity. I'm sorry, we're going to do a ratio of their areas. So I'm going to do, let's do little to big, little to big. So little will be the numerator and big will be the denominator. So the first one, we're doing ratio of their areas. So that would be what? BH over 2. That's the little one. And the second one would be what? EK over 2. Okay. All right, so now when we do our numerator over denominator, little to big, right, we get that thing. And if we did a copy dot flip, well, some things cancel, but some things don't, right? The 2's cancel, and you're left with this, okay? So what does this basically say? That says if you have two similar triangles, BH, right, that would be the product of their base and height of one over the base and height of the second one. Okay, make sense? All right, we're going to continue this one for a little bit longer. So think about this. Think about this. We just found that if two triangles are similar, you get this. Okay, so that was a lot of work. We need to write some of this down. So this is, I mean, technically what we did right there is we proved some things. So if two triangles have the same height, and this should go in your book of truth. So if two triangles have the same height, then the ratio of their areas equals the ratio of their bases. That was the first thing we did. If they have the same height, then the ratio of their areas equals to base 1 over base 2. Okay? And it doesn't matter which one's base. It can go large to big or big to large. Either one's fine. Okay? That was the first thing we did. The second thing we did is that if two triangles have the same bases, then the ratio of their areas also equals the ratio of their heights. Okay? So we had height 1 over height 2, and once again, it doesn't matter which one what order you put those in. Okay, and then lastly, if two triangles are similar, then the ratio of their areas equals the square of their scale factor. All three of them start with the same premise, right? And the premise is that if you make a ratio of their areas, okay, that certainly is a lot, right? Go ahead and pause the video. Make sure you write that down. That was definitely a lot, definitely a lot. But this is basically what it says. It says if you have same heights, right, or you have same bases, or you have similar triangles. So we're going to look at three problems where one deals with heights, one deals with bases, and one deals with similar triangles. And homework is something like this. All right, well, let's see how this works. Let's do an example. So I got a trapezoid, and basically I connected the corners, not two non-consecutive corners of trapezoid, so I make that little hourglass shape. And I made lots of triangles there, okay? So consider the two triangles, the top one and the bottom one, right? The darker orange one and the light yellow one there. We've got some distances there, just of one of the sides. Well, can you tell me about those two triangles? Well, let's see. We're also given that because it's a parallelogram, then we have alternate interior angles are congruent. Therefore, we can basically, and we got vertical angles there, so we could basically assume that those are similar triangles. We can get that through the angle-angle similarity. So we have similar triangles. Why? Well, vertical angle and the two that are labeled there, or the fact that we know it's a trapezoid. Okay? All right, so the triangles are similar. So what did we just write down about if two triangles are similar, then their ratio of their areas is equal to the scale factor squared. So what's the scale factor here? You pick two corresponding sides. Two corresponding sides. Oh, let me write that down. So if we know that two triangles are similar, then the ratio of the areas of the triangle is equal to the scale factor squared. Okay, so we got two similar triangles. So we just need the scale factor. What's the scale factor? You go to two corresponding sides. Well, this one's kind of easy because there's only one side that's listed there, right? So the scale factor is 3 to 5, small to big, or 5 to 3, big to small. And either one works. We'll do little to small. So little to small will be 3 over 5, and this formula tells us that their ratio of the areas will be the scale factor squared. So in other words, 3 over 5 squared. Well, 3 over 5 squared would be 9/25. So that is the ratio of their areas. The ratio of the areas is 9/25. Make sense? Okay, so there is one example if the triangles are similar. We're going to do one where the heights are similar, or where the heights are the same, and where the bases are the same. Okay, and I'm going to use the same shape throughout. We're just going to pick different triangles that are formed here. Okay, so same shape, right? This time I'm going to do triangle COD. Can you see COD and AOD? AOD. Okay, so to make it a little bit easier, I'll draw those two triangles. This is from the book. I'm not sure why they use different colors, but don't confuse the two colors. So those are just those two triangles that we're trying to compare. And notice if you look at those two triangles, they share the same height, right? We'll just call it h. We don't know what it is, but we'll call it h. And where am I getting that 3x and the 5x? Well, here's that explanation. We do know that the side that it's labeled 5x and the side that is labeled 3x are part of the problem from the previous one. That's part of the, I don't know, the orange one and the light yellow one that we already know their scale factor is 3 to 5. So since I don't know how long they actually are, but I know that they have to be in a 3 to 5 ratio, I just call the unknown portion of that x, which would be, it's just some number. I don't know what that number is, but I do know that when we write the proportion, it has to be 3 over 5. So I can just attach an x to it. Okay, hopefully that makes sense there, why that x is there. Okay, so let's see. What do we have here? We have same heights. And from the previous book of truth, we wrote down if the heights are the same, then the area of their ratio, or the ratio of their areas is the base 1 over base 2. Well, base 1 is, now depending upon how you want to compare this, I'll compare, let's see, yellow to green. It would still work with green to yellow. We would get a different answer, but it would still be the same, I shouldn't say the same proportion. It will be a different ratio. It'll be a different answer, but it will apply to the same problem. There we go. Okay, so for this one, I'm going to go yellow to green. Yellow to green would be 3x over 5x. Those are the two bases. The x's would cancel, and we would get 3 to 5, which is what we expected to get, right? 3 to 5. Okay, that's how that one works if the heights are the same. All right, so the one we left off was if the bases are the same. So let's see. It's asking us to look at triangle OAB. OAB, that's the yellow one. And then DAB. DAB is, I don't know, the large one that's made up of the yellow one and the white one. So I'll draw that one there for you. Okay. And I'm not sure why. This is from the book once again. Why they made it green now, right? But they did. And they also added that other piece just to show you that the triangles have the same bases and they certainly have different heights. Okay. So, and the reason why it's 3 to 5 once again is that from the original triangle, originally we showed that the ratio or the scale factor was 3 over 5, so they know that their heights must be 3 to 5 as well too. So that's why that dotted line there for the red triangle is there, just to show you that that height there of that orange one must have a ratio of 3 to 5 as well too. Now they could have used x instead of y as well too. And the reason why that y is there is because we don't literally know those two distances, but we do know that when you simplify it, right, whatever the height is, you have to get a 3 to 5 ratio or a 5 to 3 depending upon how you compare those two. Okay. So ignore the red part there for a second. We are literally just looking at the green and the, I'm not sure why the colors are all messed up here, but once again, it's from your book. Okay, so those are the two triangles we're going to compare. These would be two triangles that have the same base. They share the base AB. Remember, I'm talking about the green and the other shaded one, whatever color that one is. So these are two triangles that have the same bases. We know from our book of truth, if two things share the same bases, then we simply put their two heights in a proportion. So we'll do small to big. So the small one is the bottom one, and the larger one is the two shaded ones put together. Well, let's see. The smaller one has a height clearly of 5y, but the larger one, remember the larger one is made up of the two shaded triangles, not the red one, but the two shaded. Well, check it out. That would be 5y plus 3y, which would be 8y. So we get 5y over 8y. Can you see where I'm getting those two numbers from? Y's cancel, and so there we go. We get 5/8. You're like, why isn't it 3/5? Well, remember, these are not two triangles that are similar, okay? All right. Okay. Well, that wasn't too bad. What I just stated were not part of a theorems, although they certainly could be. I've seen them in some books written as theorems, but they choose to write a theorem that involves something else. Kind of a little bit of what we've done and some other stuff. Okay, so all this wraps together in what's called Theorem 11.7. And it says if the scale factor of two similar figures, so triangles, any polygon, any actually figure, so it could be two circles as well too. If the scale factor of two similar figures is a to b, then the ratio of the perimeters is a to b. Well, we've proven this one actually before. We proved it for triangles, we proved it for polygons as well too, and we proved it for circles. So this just kind of just rolls everything into one statement here. So if the scale factor is a to b, then the perimeters are a to b. Okay, and what we just proved is we said that if you have two figures that have the same areas, then it's their scale factor squared. So in other words, if the scale factor is a to b, then the ratio of their areas is a squared over b squared, or ab squared, the quantity ab squared. All right, so those are that absolutely needs to go in your book of truth right there. And I'll just say the majority of homework is done about these two statements. They're going to give you the scale factor, and they're going to say, well, what's the ratio of their perimeter, and what's the ratio of the areas? So the homework isn't too bad, literally, if you understand these two statements. So if the scale factor is 3 to 4, then the ratio of the perimeters is 3 to 4. If the scale factor is 3 to 4, then the ratio of the areas is 9 over 16. Okay? I'm not sure what why they. All right, we'll do one example right here. We know that we have it says we have two similar figures. So I've got a small drawing of Texas and a big. I have no idea why they chose Texas. And we know that if we know that their scale factor is a to b, then we know their perimeters are also a to b. So therefore, scale factor here, if I go from small to big, is 8 to 12. Therefore, we know their perimeters must also be 8 to 12. Now, you can reduce the fraction, obviously, so divide everything by 4, we get 2 to 3. So there is the ratio of their perimeters, 2 to 3. I do not know if that's, I literally didn't measure this one. We'll have to trust the book here. All right, how about the ratio of their areas? Well, we know the ratio of the areas is a scale factor squared. So you could do this the hard way, right, which is, what, square 8 and 12, right? Do some reducing, right, and you finally get to 4 over 9. Or, right, we already reduced the perimeter to 2 over 3, just square 2 over 3, and we get 4/9. Tonight for homework, most of your homework is going to be like this. They're just going to give you either they're going to give you the area, the ratio of their areas, or they're going to give the ratio of the perimeters, or they're going to give you the ratio of their scale factors. You're just going to have to convert from one to the other. Just remember, if they give you the areas, that is the scale factor squared. So you'd have to take the square root of both. Square root of 4, square root of 9, you get back to 2/3. Okay, makes sense? All right, so that wasn't too bad. Like I said, I think the homework's kind of medium this time. But if you do run into any problems, make sure you send me an email. I'd love to help. All right, so that does it for today. Here's your homework. You guys have a great weekend. Send me an email if you need some assistance. Like I said, I'll probably not check it every single minute on the weekend, but I certainly will reply to you if you send me an email over the weekend. So have a great weekend, and I will see you guys on Monday.